Okay guys, so we're going to start talking about design methods now. And design methods, actually, before I move on to this slide here. So one of the purposes of this course is to kind of bridge the gap from statics to structures, right? So again, in statics, we learned a lot about external forces. In mechanics of material, we're going to learn about the effects, the internal effects of those forces in the form of stress, which we've been talking about already. And the goal of this class, really, or the goal of engineering in general, is to be able to design systems, right? We want to engineer or design systems. So we have a couple of different design methods, and these design methods are outlined by design codes. Design codes. Okay, different types of materials have different design codes that you need to follow. We also have the California Building Code. We have International Building Code. We have different types of codes that we need to follow. And you guys will learn a lot more about codes as you progress in your coursework. Okay, so for example, in steel design, you'll use AISC, American Institute of Steel Construction. In concrete, you'll use a different code book and so on. So each material kind of has its own code book that we need to follow. So what we're going to do today, I'm going to introduce you to a couple of different design methods that you'll find within the code and kind of talk a little bit about them, okay? So the first design method that we're going to talk about is called the allowable stress design, okay? Or for short, we call it ASD. So we now, up to this point, know how to calculate the maximum load that an element can carry. Right? We've been doing that in the previous examples. We want to see what the maximum load that the element can carry is. So as engineers, let's think about this. Let's say we have a beam here, okay? And let's say, you can even think of this as like a 2x4, like just a timber, like plywood, 2x4, anything like that, okay? So just think of something that you know and that you can imagine in your mind. And let's say you decide to walk on this plank or this 2x4 or whatever kind of beam you're imagining, and it's stable, it doesn't break. But then you and your friend decide to walk on it. Okay, and then you and 3 friends decide to walk on it. The question is, at what point, right, we're going to reach some maximum load to the point where the beam or whatever you guys are envisioning is going to break, right? We're going to lose that structural integrity, okay? So we know we can apply some max load, okay? Now, the question is this: do we design our structure or our system, our element? Do we design our element to be able to carry this max load or not? Okay, let's say we do. Let's say we have determined that the maximum load on whatever we're designing is 1,000 pounds, and we design it that at 1,001 pounds, this system, you know, it loses its structural integrity at 1,001. So it cannot go over 1,000 pounds, which is the max, okay? What's going to happen if our measurements weren't 100% correct? Or what if during construction we're a little bit off and there's some type of fabrication error, okay? What if there's some unaccounted for vibration or a potential slight increase in loading? For example, we have maximum limits for buildings. What if one day we go a little bit over the max and no one's counting those fire code regulations, okay? These are all things that you want to think about, right? So the point that I'm trying to make here is no, we don't ever want to design exactly for that maximum load because we always want to be safe, right? We want to design these structures to be really safe for the people who are going to be using them, the general public, right? So we want to build something called, or integrate something into our design called a factor of safety, which brings me to this slide here. So in order to account for all of these potentials, what we do is we say, okay, so we know what our allowable is, we know what the fail is. We're going to use this factor of safety here, which is basically a ratio of our failure load to our allowable load. The failure load is found from experimental testing of the actual material. So in Mechanics of Materials lab, you're going to be testing different types of materials to their limit. How far can I push this timber beam? How far can I load this concrete element in compression before it cracks, and so on. So we get these from testing. Okay. And our factor of safety is based on experience with the material. So we get these from the code. We get both of these really from the code. Okay. And then we can determine what our allowable force is and make sure that we're not exceeding that in the design. Okay. Now, allowable stress design, ASD, right? You might have noticed that there's a key word here, which is stress. So if the load is applied to the member and it is linearly related to the stress developed within the member, which is the case for all of our problems right now, we can also express our factor of safety in terms of stress. So we can say it's also in terms of sigma fail divided by sigma allowable. And we can also write it as tau fail over tau allowable. Okay. Now, our factor of safety has to be greater than 1, and I think that makes sense here, right? Because we never want our allowable to be greater than our failure, right? We can't have that. That means we're going to under-design the system. So it has to be greater than 1. These factor of safeties are determined based on different things, and they can always be found in the design code. So I will give these to you in the problems, because anything that the design code gives you, I'll provide you. And then basically a design based on allowable stress limits is called allowable stress design, ASD. Okay. Now, that's all ASD. The second type of design method that we use and that you'll see in the code is called LRFD, or load and resistance factor design. Okay. The big difference, before I get into these, the big difference here is that LRFD separates or splits up the uncertainties. So let me explain what I mean by that by pulling back here for a second. Remember how I said that we want to deal with measurement errors and fabrication errors and potential vibration or increase. And we kind of take all of these factors in ASD and we plug them in and we come up with this factor of safety. This is given by the code. LRFD says, okay, no, I'm not going to just put everything together. I'm going to have different variables that account for different uncertainties. I don't want to put all of this into one factor of safety. I'm going to split them up. So I'm going to have something that accounts for load factor uncertainty, for resistance factors, and for design criteria. Okay, I'm going to go over each one of these in the next couple of slides. So the first area of uncertainty is in loading. So we have something called load factors, and this little Greek letter here is gamma. When I write it like this. Okay, so gamma here, what we do is we multiply basically our gamma by the loading that we calculate. Okay, so let me write this here. Okay, so let's say, for example, I have some total load. I'm going to call the total load R, okay? And I have the total load would be equal to whatever my dead load is, plus whatever my live load is, plus maybe whatever my snow load is, let's say. Okay, this is how we would build a system. We'd have to account for all of the loads on the system, right? Okay, so what LRFD load factors do is they say, you know what, I'm not just going to add the dead load, the live load, and the snow load. I'm not going to just add these loads together. I'm going to multiply them. I'm going to multiply them by a factor. So I'm going to make this 20% more. I'm going to increase the live load by 60%, and I'm going to reduce the snow load by a little bit. Okay, so this is a little different than ASD, where in ASD, our factor of safety had to be greater than 1. Our gammas don't have to be greater than 1. And the reason for that is these gammas are based on probability that the loading will occur for all of the events stated here. Okay, so let me pull back and explain this a little bit better. Let's say we have a building. Let's say this is an office building and we have multiple floors here. Okay, let's say we're looking at one of the floors. I'm going to try to draw 3D the best I can. Okay, let's say we're looking at one of the floors and we say dead load. I'm going to pull back and explain what dead load is because I'm not sure if all of you guys know what this is. Dead load is like the self weight of the building. Live load means like people. How many people are in the building? And of course, snow load, it's actually a type of live load, but it's really just snow. It's like a gravity load. Okay, so what LRFD is saying it's really unlikely. Okay, take the dead load out. The dead load is there regardless. It's going to be there all the time. It's present all the time. So let's increase it by 20%. Okay, the live load, the amount of people that are coming in the building, Well, that's also a little tricky because although we have limits, what if some more people come? Or what if our average estimate of weight is a little bit off? So we're going to increase this by 60%. Okay. Now, why are we decreasing the snow load here? Because this is the logic in terms of the probability that's used. It's highly unlikely that we're going to max out our live load and increase it by 60% on the same event that all of the snow load will occur in the building. Okay, so based on probability, we're going to actually decrease the snow load. There's a lesser chance of our maxing out of the snow load, and we're going to increase our live load, and we're going to hope for the best in this case, okay? But we've done a lot of probabilistic scenarios in the code and a lot of simulations to say that this is a highly unlikely event that all of these will happen together, so we're going to kind of leverage these, okay? Next here, we have resistance factors. So for resistance factors, we use this Greek letter called phi. We spell it P-H-I. And this is also determined from probability, but this is determined from the probability of material failure related to quality and strength. Okay, so I'm gonna give you guys an example of this. So for concrete, you'll see that we have smaller factors in steel. And the reason for that is because we are not as confident in the behavior of concrete as we are in steel. Okay, concrete has a lot of variability in how it's mixed, how much water content there is, the gravel content, the coarse ratio, all of these different kinds of things. So our typical phi value or phi value for steel is 0.9, okay? And you'll find smaller values for concrete in terms of phi, okay? The last category we have is once we've determined gamma and phi, we need to make sure that our member strength is greater than the load we're applying. That makes sense, right? You want to think of it like this. Let's say you're at the gym, and let's say your bicep has the strength to carry only, or to lift only 30 pounds each bicep. Okay? You can only lift 30 pounds per bicep. What's going to happen if you pick up a 40-pound dumbbell? Your bicep will fail, right? If you are sure that's your max weight, you cannot pick up a heavier one. You're not going to be able to do the curl, right? So you need to make sure that the member strength, in this case, that example would be your bicep, is greater than the load that you're trying to load your bicep with, right? Same goes for structural members. Okay, so the member strength, how do we measure member strength? By something called PN. We call this the nominal strength of the member. Okay, here is where we multiply it by phi. So what we're doing is we're saying this. Let's say your bicep, remember, each bicep can carry a 30-pound dumbbell. What we do, let's say phi is equal to 0.8 for your bicep, right? We're going to say, you know what? Let's decrease how much you can actually carry. Let's make it 30 times 0.8, which is 24, just to be safe. So you see how we're making this a safer system right now. Okay, so we'll say we're going to decrease it by this phi. We're going to decrease our member strength, but this needs to be greater than or equal to the sum of all of our loads times gamma. So our dead load, our live load, our snow load times all of those gammas, and basically our phi reduces the nominal strength and needs to be greater than the applied load. So strength greater than load. And again, ASD combines all these uncertainties into a factor of safety, whereas LRFD likes to split them up and use a little bit more of a probabilistic method to solve for them. Okay, so let's do this example. We have a control arm that's subjected to the loading shown, and we want to determine to the nearest quarter of an inch the required diameter of the steel pins at point A and C if the allowable shear stress for the steel is high. So this is a little different. The problem is providing us with the allowable shear stress here. Okay, so of course the first thing I'm going to do, I'm going to go ahead and right on this picture draw my FBD. I have some force here, BA. I have a pin here, CY, CX. I have 3 kips and I have 5 kips, right? So the first thing I'm going to want to do here, I need to first solve for the reactions to figure out what's happening in this system. So I'm actually going to sum my moments about point C, counterclockwise is positive. That gets rid of those 2 pin forces for me. And I get FAB times 8 inches minus 3 times 3 inches minus 5 times the 3/5 component times 5 inches equals 0. And I get FAB equals 3 kips. I'm going to continue solving. Sum of Fx equals 0. This direction is positive. I get negative 3 kips minus Cx plus 5 times 4/5 equals 0. And I can solve for Cx as 1 kip. And of course, my last equation of equilibrium is sum of forces in the y direction equals 0. I have Cy minus 3 kips minus the component 3/5 equals 0, and I get Cy equals 6 kips. Okay, now I need to use that tau allowable to solve for the diameter. So I'm going to first start by writing that equation out. Tau is equal to my shear divided by my area, right? And at the pin at A, let's check. They're telling us here, the pin at A experiences single shear. I don't need to divide by 2, whereas the pin at C experiences double shear. So we first need to figure out, what is V at A? What is V at A? Well, I just solved for that. V at A is 3 kips right here. So I actually have everything I need to solve for A here. So my tau allowable was given as 8 kips per inch squared. That's equal to 3 kips divided by the area. And I can solve for the area here. I'm actually going to plug in, instead of just solving for this, I'm going to say 8 kips per inch squared equals 3 kips divided by pi times the diameter over 2 pi r squared. And I can solve here for the diameter is equal to 0.691 inches. That's dA. Okay. Now I'm going to do the same thing for pin C, except it's double shear. So at C, my shear is going to have to be the resultant of these two. So let me first start here. The resultant at C is equal to the square root of 1 squared plus 6 squared. So I end up getting 6.083 kips. So my VC is going to be 6.083 kips divided by 2 because it's double shear, and I get 3.041 kips. And of course, my tau allow is equal to V over A, which is 8 KSI equals 3.041 kips divided by pi times DC over 2 squared. And I can solve for my diameter of C as 0.696 inches. And let's not forget, it asked for the nearest quarter of an inch. So for both of these, I'm just going to say for both of them, I can use 3/4 of an inch, 0.75. That's the closest roundup I can do. Okay. All right, let's move on here. Oh, and here's a picture of the shear at A and the shear at C. So we have the single shear and the double shear for each of those values there. Alrighty, let's go ahead. Let me see how many more examples there. Let's go ahead and do this last example, and then you'll have one more video to wrap up this topic here. I know it was really long, so if you got through to this point, you're already doing well. Okay, so here, this is a really good example actually for LRFD, so let's go through this one. We have a 400 kilogram uniform bar. So the fact that it's giving us the weight of the bar means that we need to include that in our free body diagram. Okay, that's a kind of a heads up there. Okay, it's supported by a steel rod AC and a roller at B. If it supports a live distributed loading of 3 kilonewton per meters, determine the required diameter of the rod. The failure stress for the steel is sigma fail is 345 MPa, and we're being told to use LRFD, and we're given our resistance factor, and we're given our load factors. So we're given all the information we need to perform the analysis using LRFD. Okay, so I'm going to start by drawing the FBD directly on this diagram. Remember, we were given the weight of the beam, so I'm going to take the center of gravity here, and I'm going to, we're given the mass actually, so 400 G. Okay. And here I need a force FB, and of course I have the resultant of this, which is just 6 kilonewtons. Okay. Okay. So the first thing I want to do here is I want to multiply this gamma D and gamma L into the loads, right? Because right now I have the unfactored loads. So this is the FBD with the unfactored loads. Means I have not multiplied in gamma D and gamma L yet. So what I want to do here is I want to go ahead and redraw my FBD with my factored loads now. How do I get the factored loads? Well, I need to just multiply gamma D and gamma L. So what is the dead load here? Dead load means it doesn't move. This would just be the weight of the bar. So the dead load in this case, D, I already wrote it down here, is 401. Okay. And you see, that's equal to 3.924, yes, kilonewtons. 1.2 times D is equal to 4.709 kilonewtons. Why am I multiplying by the 1.2? Because it's telling me in the problem that gamma D is 1.2, so I need to multiply that by the dead load. I want to increase it from what it actually is. Okay, now the live load is going to be, they're telling us in the problem, a distributed live load of 3. So I'm going to take that 3 and I'm going to multiply it by the 2 to get the resultant. Or you don't even have to do this. You can either do it with the 3 or you can do it with the 6, the resultant. So it doesn't matter. I'm multiplying it by 1.6. So 1.6 times 6, I end up getting 9.6. Okay. Now I'm going to redraw my FBD here. That did not work. Okay, there we go. With my new factored load. So I have the 9.6 kilonewtons. I have the 4.709. I have FAC. And I have FB. Okay. Now I'm going to use this diagram. And I'm going to come here and I'm going to sum moments around point B, set that equal to 0. 9.6 times a moment arm of 1 plus 4.709 times a moment arm of 1 minus FAC times a moment arm of 2. And I can solve for FAC as 7.154 kilonewtons. Okay, now the nominal strength of the rod is determined from this equation. My nominal strength is equal to sigma fail times A, right? This is just sigma is equal to force over area. Force here is that Pn. Okay, and my phi is 0.9. That was given. So I know that phi, Pn, needs to be greater than or equal to FAC. I know what Pn is, right? So I'm just going to plug everything in here. 0.9 times my sigma fail, which was 345 times 10 to the 6 MPa, times the area of AC needs to be equal to the 7.154 times 10 to the 3. I'm putting everything into newtons here. And I get area of AC is 23 times 10 to the 6 meters squared, 10 to the negative 6 meters squared, which corresponds to 23.04 millimeters squared. And I want to solve for diameter, so pi r squared. And I get 5.42 millimeters. Okay, that is it. So please review these examples if you had a little bit of trouble with them. And then the last video is going to go over strain and kind of finish up from there.